Welcome back, everybody. So the last couple of classes, we've been thinking about the fundamental theorem of line integrals for gradient fields and seeing how the fundamental theorem of calculus, part 2, generalizes in the situation where we're integrating over a curve in space. Well, today we're going to ask the same question, but in a new context. We're going to think about how the fundamental theorem generalizes when we're integrating not over a curve, but over a region in the xy plane, some two-dimensional region like this over here. And it turns out we need to rethink things a little bit. If we go back to the fundamental theorem, part 2, right, here's what it says, right? Integral of f prime from a to b equals f of b minus f of a, which we have been thinking about this as the net change in f, right, over that interval. But the thing is, if we are integrating over a region in space, right, what does that really mean, the net change in f? We don't really have a starting point and a stopping point anymore. And so this point of view doesn't directly generalize into our new situation. So we kind of have to go back and see FTC2 from a different perspective. And so here's one way to look at FTC2, right? So on the left-hand side, this integral is telling us, well, that we can march through our entire interval from a to b and add up our derivative information all along there. And that's what this integral on the left is giving us. But FTC2 says, well, you could do that, or right, you could just do the right-hand side. And this really is just looking at our function information on the boundary of this interval, these boundary points. And I claim that this is really the way to think about FTC2 that generalizes. On the left-hand side, we're saying that, hey, we can go through our whole interval here, adding up our derivative information, or we can look at just the boundary of our interval. That's what this little del means, the boundary of our interval, and add up our function information. Right here, I'm using the integral symbol in this situation to just mean adding stuff up. This parenthetical with direction, where this is coming from is the fact that we don't just have f of b plus f of a, right? We have f of b minus f of a, right? And so this this distinguishes our kind of our endpoint of our interval from our starting point of our interval. And so somehow this right-hand side is remembering the direction that we moved through our interval, right? In this case, from A to B. And so the FTC2, in kind of this general way of thinking about it, says we can integrate over our whole interval, adding up derivative information, or we can just add up function information on the boundary if we include some direction information in a proper way. And it turns out that this here, this is going to be our general way of thinking about FTC2 that we can take with us and see how it generalizes in a number of different situations. Right? Starting right here with the situation we're in, thinking about a region in the plane. And so the result that tells us this generalization here is called Green's theorem. And so it looks kind of ugly. We're just gonna just say a few words about it and put it to work, and then we'll kind of circle back and talk a little bit more about the meaning here. But so Green's theorem, in a nutshell, says, well, if you have a region D in the plane, well, you can go through that whole region D, all right, this whole two-dimensional region. I'm adding up this information, or you can do a line integral around the curve that is the boundary of D, adding up this information. And so here, this curve, this is the boundary of our region D. And so it's a little bit hard to see here, but I claim that this is, of this form from the FTC2, right over on the left, right? This is somehow playing the role of, integral over some region of derivative information. Right here we have our partial derivatives going on, and over here on the right, this integral, this is telling us what we can integrate instead along the boundary of our region, adding up just function information, right? And so here we have just P and just Q. A couple notes I want to make about this equation here is first, and we mentioned just a moment ago that we need to somehow move along the boundary in a proper direction. And what that means for Green's theorem is that we want to move along this boundary curve counterclockwise. All right, so moving along like this is how we need to parameterize our boundary curve in order for this line integral to exactly match up with this double integral. If we parameterize the other way, then it would end up being the negative of what it should be. And there's a little bit of notation that's sometimes used for this moving around in counterclockwise direction around our curve. Sometimes on our line integral, we'll actually do a little loop with an arrow showing us that we're moving counterclockwise. And so that's just, if you see that, that's just telling you the kind of orientation that you want to move along your curve with. Green's theorem also assumes some niceness on our region and on our functions P and Q, but we won't get into the details there. The next note I want to make before we dive in and look at an example is that Green's theorem is an equation, and like any equation, we can use it to swap out the left-hand side for the right-hand side, or the right-hand side for the left-hand side. And Green's theorem, it turns out, we usually use it right to left, where we take a line integral and swap it out for the double integral that Green's theorem says it equals. This is often a cleaner integral to work with than the line integral. All right, well, let's put it to work. I'm not going to scroll down all the way yet to see the whole curve here, because I want to give you a chance to work on this. So here we have a line integral, right? This is actually what we call a projected line integral, because we have, instead of ds, right, we have dx and dy over here. And so we have this line integral, and we want to compute it around this kind of triangular curve here, right? It starts at the origin and then moves along like that. Pause the video and see if you can use Green's theorem to swap this line integral out for a double integral and see if you can compute what we're left with. All right, well, let's talk about this one. So, using Green's theorem, I just scrolled down and lost it. Let me move back up. Right, that this line integral for p dx plus q dy swaps out for the double integral of qx minus py. All right, and so here we do have a line integral of that form. We just have to figure out what our p and q are. And if we look up above, the p is what we're calling the function next to our dx. And so that's going to be this x y squared, and our q is what we call the function next to the dy. And so there's our p and our q. And Green's theorem says that this line integral is equal to this double integral of qx minus py. And so here, at this point, we just have a couple of partials to compute. So q with respect to x, 2 comes down. We're left with 4xy. P with respect to y, 2 comes down, and we're left with 2xy. And those match up nicely. So if we have 4xy's and subtract 2, then we are left with 2xy's. And to integrate here, we just need to set up our limits of integration, right? And recall we're just integrating over the region D, right? And where we get that, once we have our curve, and notice we are moving counterclockwise around this curve for our line integral. That's the right direction for Green's theorem. Right, D is just all the stuff inside. All right, so there is our region D, so that triangular region inside. And so to get our limits of integration, probably going to be cleanest to think about rectangular coordinates as opposed to polar. And so we just need to think, hey, do we want to set x move y or set y move x? And well, if we imagine setting y and moving x, well, down here we'd start x at this slanted line, end at this slanted line, but up above we'd start x at the slanted line, stop x at this vertical line, and so we'd need 2 different integrals. And so here it's going to be cleanest to think about setting x and moving y from this slanted line to this slanted line. And notice those are going to be our instructions no matter what x down here we pick. Always going to be starting y at the bottom slanted line and stopping it at the top slanted line there. Right, so here we just need equations. For our bottom line, goes to the origin in 2, 2, and so this is a line with slope 1 through the origin, just y equals x. Our top line here goes to the origin and to 4, so that has slope 2, so our equation there is y equals 2x. Right? And so those become our starting and stopping instructions for y. And then for our outside integral, right, as always the question is, hey, well, what x's are we doing this for? And looking at the shadow down here, right, we're doing this for x's from 0 up to 2. And so at this point, everything's set up. We can integrate what we have in terms of y. We then just work through this double integral. I'll let you work through those details. At the end of the day, what we get to is 12. A couple of notes I'd like to make about this example. First of all, notice that the only place that we actually used Green's theorem was at the very start, right here. We only used Green's theorem to take this line integral and swap it out for this double integral. All right, once we have this double integral, we just need to figure out the function we're thinking about and our limits of integration, just like we would any other double integral. So here we really just use this theorem to make this initial swap, and then we get to work. The second note I want to make is that indeed this did save us a whole lot of work. Imagine, if we needed to compute this line integral, in our standard way. Well, how do we compute any line integral? And we have our 1-2 step process, right? First step is parameterize our curve. And here our curve is actually 3 different pieces. So we'd have 3 different parameterizations, 1 for each piece. And then after we had those, our step 2 is to translate our line integral. And so we'd actually have 3 different line integrals to translate and work through, whereas Green's theorem says, don't worry about that. Just swap this out for this nice clean double integral, which we can work. So I'd like to talk now a little bit more about the meaning kind of driving Green's theorem. Specifically, let's look at kind of what each side of the Green's theorem equation right here, what each side of our equation is adding up. Okay. And so to start, let's look at the right-hand side. This line integral for this projected line integral that we're looking at. Or really, written like this, it's the sum of 2 projected line integrals. All right, and that in that form doesn't feel very natural, but what I claim is that this line integral, it equals this line integral here on the right, on this line integral of a vector field. Right, where the vector field has as its components our functions p and q. And so here this is a line integral for a vector field. All right, and line integrals for vector fields, we have kind of a physical interpretation for what these are adding up as we move around our curve. And recall the information that a line integral for a vector field is collecting and adding up are the tangential components of our vector field vectors. And so here a line integral for a vector field, right, adds up tangential components of our vector field vectors. And so the picture over here on the right is that this vector field PQ is giving us, arrows. I'll draw it in green. Right, green arrows. Each point, in the plane, both in our region D and outside of our region D, we have all these different arrows. Maybe there's one over here. It goes like that, and so that's what our vector field is giving us. And this line integral over our curve C, right, takes us and marches us along our curve in the counterclockwise direction, right? And at each point, say this point, we have our unit tangent vector pointing in the direction we're heading. And we ask, well, how much of our vector field vector is in that direction, right? I'm going to look ahead and grab that tangential component, right, that we get by projecting this green vector onto that direction, right? And so this here, the signed length of this box here, right? This is one of the pieces of information that our integral is thinking about, right? And we're going to march along our curve, and we'll do that at every single point. You know, here we'll have a unit tangent, and we'll grab the tangential component there. And similarly, over here at this point, we'll have a unit tangent vector, and here when we project, right, the tangential components behind us, and so this one will be counted negatively. Right, and we're just going to march around the curve and add up those tangential components. But if we think about these kind of green vectors as describing how some fluid is moving, let's say we have some kind of like circulating fluid moving around, maybe like we imagine this as like a thin sheet of fluid. Well, then moving around this curve and kind of grabbing these tangential components, that's like asking, well, how is this fluid circulating around this curve, right? Is it mostly going in the same direction that we are, counterclockwise? Or is our fluid mostly fighting against us, right? Is it kind of moving clockwise? And that's what this integral is going to be handing to us. It's the physical name that we give for what this is computing is the circulation around our curve. And this is the physical interpretation. If it's positive, telling us our fluid is coming along the same direction, counterclockwise. If it's negative, then it's mostly moving the other way. So this line integral, written as a vector field line integral, has a nice physical interpretation as the circulation of our fluid around our curve. A second note about this is that the proof of this equality is not like some super deep thing. It actually can be proven very quickly if we just use our little catchphrase on each side, right? Our catchphrase is, what is it again? That's right, it's multiply by 1 over dt. Right, and if we do that here, and then we distribute this dt to the dy and the dx, and over here, if we work out the derivative of our parameterization with respect to t, and then do the dot product, we just see within about a minute that, okay, these two sides are the exact same, and so they equal each other. Okay, so that's how we can think about the right-hand side over here, telling us about circulation of this vector field around our curve. Let's think now about this left-hand side. And what I claim is that this qx minus py function if we plug in some point, like let's say like this xy point, into this function qx minus py, that this also has a nice physical interpretation, that it's telling us the circulation of our vector field at that specific point. And so the idea here is, you can imagine, we got this fluid circulating around, and if we somehow kind of nail down at this point a fidget spinner, right? We nail it down, so it's centered, it's fixed in place, and then we just kind of let go and see what happens. And because of our fluid kind of moving around, right, maybe our fidget spinner is going to start spinning. And maybe it's going to start spinning this way, right? And maybe it's going to start spinning fast. And in that case, the circulation is going to be positive because it's spinning counterclockwise, and large because it's going fast. That's sort of the idea, that if it's positive, we're moving counterclockwise, and if this value of our function is negative, well, that would be telling us that our fidget spinner would actually be moving clockwise. And if we get 0, that's telling us that our fidget spinner would just stay put and wouldn't spin one way or the other. And so our qx minus py has this nice physical interpretation of circulation of our vector field at a point. And so if we put these two kind of physical points of view together, we get a nice kind of physical interpretation of Green's theorem as a whole. All right, and so here, I've kept the exact same left-hand side of Green's theorem, but here I've written the line integral as the line integral for the vector field, PQ. And so the kind of nice physical interpretation here is that, well, the right-hand side says, well, we can move along our boundary curve C, right, going counterclockwise, and find the circulation of our vector field along our curve. So we can move along our boundary curve counterclockwise, find the circulation of our vector field. Or we can actually go through each point inside our region, and I'll just try and draw a little like counterclockwise loops here. Add up the circulation at every point through our region. That's what Green's theorem is telling us. We'll get the same thing if we go around the boundary and compute the circulation of our vector field there, or move through our entire inside of the region, adding up circulation at each point. Okay, so that's a little bit of kind of physical intuition for what's going on with Green's theorem. Let's do one more example. So let's use Green's theorem to compute the line integral for a vector field, where our vector field is right here, and we're moving along this curve here, the boundary of the unit square in the counterclockwise direction. Pause the video and see if you can, once again, use Green's theorem to translate this line integral now of a vector field, to swap it out for what Green's theorem says it equals, and see if you can work through computing the integral we're left with without doing any integration whatsoever. All right, let's talk about this one. Right, well, our vector field is a vector field on the plane, and right, this is indeed the form that we have on the right-hand side of Green's theorem, right? Just the line integral for a vector field, and that's exactly what we have here. F is some PQ. And what Green's theorem says is we can take that line integral and swap it out for a double integral. Right, and so here I've just taken our starting line integral here and used the fact that f is actually some vector field PQ. At this point, we can use Green's theorem to take that line integral for a vector field and swap it out with this double integral of qx minus py. And now we just have a couple of partials to compute. Qx, all right, what do we get here? We're going to get 2x, I guess, and py, we're going to get 2x. And so subtracting those, we get a nice clean 0. And if we march through our region D, adding up 0, we're just going to get 0, right, as our net volume. And so we don't even have to, set up our limits of integration or anything like that. We can see right away, if we integrate 0, we're going to get 0. Now this example has a nice connection with some ideas that we've seen before, right? Right here, in this step, we saw that our qx minus py is 0. And I claim that that tells us something. What does the fact that qx minus py equals 0 tell us about our vector field f? If you said that it's conservative, then you are spot on, right? The idea here, qx minus py equals 0, well, that's the same thing as qx equals py, right? This is an equality of our cross partials here, right? Q with respect to x and p with respect to y. And so here, this is showing us that f is conservative, right? Or in other words, a gradient field. And so with that in mind, right, it should make a lot of sense, well then, if we integrate our conservative vector field along a loop, right, moving along our curve C, that we get 0. Right? This is one of our kind of characterizations of a vector field being independent of path, right, which gradient fields are. And so this connects nicely back to those ideas when we're thinking about line integrals for vector fields, specifically gradient fields. Okay, well, good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.